in this unit, this is the last item of that unit. I'm going to try to understand as much as we can using essentially the fundamental equality that we just saw to understand our nice example better, the y squared equals x cubed minus x. And that's a cheat. I mean, you can't do that. The fundamental equality is not meant to make you understand function field extension. It's just one equality. There are much more tools to handle general things that you will see as we go along. You will need those tools. So the point is that in this unit, this is very short. I'm going to show you how to use the fundamental equality and do like valuation calculations to get some understanding, but limited understanding. And then in the next unit, which will be after the break, possibly this will take also a bit more time, we will use more theory than you know. But I'm going to state what I need, but I'm not going to prove it today. This is just so that you know where we're heading towards and why we're doing it. Right? So I'm going to state some theorems, and you'll see they're very powerful, and the proofs are like extremely complicated and long, by the way. We'll do all of that in the video mostly. But I want you to see them in action before like doing everything and then see them in action. It will also give you some appreciation of how difficult it is to actually analyze those things. Okay, so let's see. But in this unit, we are going to do things quite simply. So again, we're looking at y squared equals x cubed minus x. At some point, I'm going to take the field to be 5, f5, like k to be a5, but for now, just keep it like that. And actually, I think you showed in the recitations or problem set that this is a function field when the characteristic is not 2. Namely, the constant field remains k. If you started with k of x and you look at f, L, like the constant fields of f, is still k. Okay, so let's see. So my goal is to try to understand what are the prime divisors in our new function field. And the strategy is, as usual, is to, like as we did in the proofs, is to look at the rational function field and go from there. So let's say that you are looking at this capital P. This is a prime divisor lying above P infinity in K of x. Right? In K of x, to understand all prime divisors, we know that every prime divisor in the bigger function field is over some prime divisor. So I'm going to go essentially one by one, like there are infinitely many, but one by one prime divisors of K of x, which you completely understand, and try to understand what's above them. Okay? Now I chose x. I mean, I could have chose K of y. There is no importance to x whatsoever. But I chose x, and I'm going to try to understand our function field, K of xy, modding out by y squared equals x cubed minus x, by jumping from K of x. And by the way, note, okay, maybe. Okay, so let's see. So here is the trick. So I'm using trickery here. It's not like I mean, it's correct, but it's not math. It's like engineering. Okay, it's like what's going on here. It requires, in some sense, much more, ideas because you don't have tools. So it's actually harder. It's like trying to build a spaceship with like a wood. So if you succeed, you're amazing, right? Anyhow, so let's look at, I don't know what is P. I don't know what this capital P, abstract capital P that lies over P infinity. But I do know that whatever it is, if I take the valuation of capital P at y squared, then it's twice the valuation of capital P at y, because that's how valuation behaves. And on the other end, y squared is x cubed minus x. It's the same element. So, these are the same numbers. And the point here is that now on the right-hand side, you have only x. So it makes sense to look at x as an element also in the rational function field below. So v capital P of this element is actually just the ramification index of capital P over P infinity times the usual infinity valuation of x cubed minus x. Right? Because this is a place that lies above this place. It has some e, which I don't know. I want to figure it out. But whatever it is, this is okay. I couldn't have done this with y, because y doesn't live in K of x. But now when I translated y to x's, you have this. And we know what's the evaluation of this at infinity. I mean, what is it? This is a question about the rational function field. And don't look. It has 3 poles at infinity, right? So it's -3. The valuation is -3 because it's like it looks like infinity 3 times, in some sense. But really, it's just the degree, minus the degree. So minus the degree is the valuation at infinity. So what you got, if you look at it for a second, that 2 times this number is -3 times that number. Right, I'm just kind of comparing things. And E is at most 2, right? I mean, what is E? What is the residual degree? I mean, we know that the sum of EI Fi is the degree extension of F over E. E in our case is K of X. So in particular, E is smaller equivalent than that. Actually, that's something that you already showed with Tomer without the fundamental equality. But this time something is even smaller. But even the sum is smaller. So this residual degree is at most the index of the extensions F over K of X, which is 2. So E is either 1 or 2. But you see, 2 times a number, everything is integers. 2 times a number is -3 times that number. So 2 must divide that. So that must be equal to 2. So we get that the ramification index is 2. And the fundamental equality tells us that that's the only prime divisor lying above P infinity. So the picture that may appear here, but no.
So the trick would be just to show that after P over P is 2.
Right, and that gave you also that that's the only place that lives above P infinity, because the sum of the EIFI is 2. Right. Exactly. So P infinity in K of X over K, there is only one place above it. And because there is only one place above it, so we always use that notation, but we can also call it P infinity. Soon we'll be a bit more, I don't know, informative about the name we choose here, but in a second. So that's like, right, that's our function field. That's K of xy mod by y squared minus aq plus x. Right, the function field and so forth, but this thing, and let's write it like that. E is 2 and f has to be 1. Because the sum of EI Fi has to be 2. There's only one place above you. So its E is 2, so its F must be 1. So the residue field is the same. It's also K, by the way, because this is a rational place. It's degree 1 place. So its residue field is K. And that's a degree 1 extension of that. So that's also K. So everything here is in K, the residue field. But you see, using this trickery, we figure out what's that there is only one place, one prime divisor above infinity. Yeah.
What is the place?
Right.
Place.
Good. In a second. Yeah. That's what I said. Will be a bit more informative about what do you mean by that, because that's currently just like a name. Like, right? How would you describe a place? Right? Like, what kind of information you need to describe a place? Like.
Yeah.
Right. Good.
I understand the place is just the relation.
Right. No. You will see 2 ways now. But let's do one more like that. That's what we did, right? So let's do one more before the break, or let's take a break. Let's take a break, and after the break, we're going to do that and also be more informative about choosing names or. So far, we just used the fundamental equality to show that there is exactly, I think it's exactly what you don't see on the board. So let me write it here. So there is P infinity and capital P infinity at the top equals 2, F equals 1, and there's no other place above it. Okay. So let's see. So now let's consider other prime divisors like 0. So P0, 0 as the element in the rational function field. Let's try to do the same trick. We will succeed. So I want to understand it, so I'm looking at functions. Right? You see, I'm using y and x to understand this prime divisor. So V capital P, for any capital P that lies over P0, on one hand, V capital P of y squared is 2V P of y. On the other hand, y squared is x cubed minus x, as before. But now capital P is over P0. So that thing is the ramification index of this p that we're trying to understand over p0 times the evaluation at 0 of x0 minus x cubed minus x. And what's the evaluation of x cubed minus x at 0? Even though it's written there, but trying, I don't know. Like how many zeros does this polynomial have at 0? 1, right? Because so it's like x squared minus 1 times x. So the product, the multiple of x that divides it is 1. It has 3 zeros, but it has 0 is a multiplicity 1 0. That's what I'm saying. The other zeros are 1 and minus 1. Assuming the characteristic is not 2, when we said it's not 2, so it's 3 different zeros. So right now, this is 1. So we are left with this number that we are kind of trying to understand. So looking at left and right, you see that E is 2 times this thing. So this means that E is 2, because E can be either 1 or 2, and 2 should divide that, so E is 2. So you see, it's not math. It's like you hope that things will work out, and it does usually. But by the fundamental equality, again, E is at most 2, so we know that E is 2 by this line. And again, over P0, you have one place above it. E is 2 and F is 1. And I deliberately don't give it a name for a moment, okay? Oh, no, that's because it is, because the characteristic, the equation that defines the function field is this thing. So as an extension, kxy modding by this over kx is degree 2 extension. Right. Exactly.
The fact that this is a prime, like the fact that 2 is prime is the key of all of that, right?
Yeah. Like yeah, if t weren't prime, then yeah, and sometimes also because it's 2, but here it's also because it's prime, right? But these are tricks. You're right. I mean, it's like these are tricks. Maybe I should say that, like you will see next time or next time, almost towards the end, that if the extension is Galois, f over e is Galois, then not only the sum of f over e is sum f I e I is equal to the extension, but actually all the e's are the same and all the f's are the same, because kind of the automorphism of the Galois kind of takes one place to another, and everything is isomorphic. So what you get is that all of them are the same. So if all of them are the same, it means that E, the common E times the common F times R is the extension. And so if the extension is prime, for example, then you have E times F times R equals prime, and there are only 3 possible choices. One of them is the prime, and the other 2 are the ones. So you can play with that also. But that only also takes you so far, and at some point you need to actually have like proper tools to handle everything. But for fun. Okay, the same calculation will show you that also p plus 1 and p minus 1 characteristic is not 2, has a 1 place above it, because I only use the fact that there is a 1 here. Right? It's a 0 of multiplicity, like 0 is a 0 of multiplicity 1 in x cubed minus x, but that's the same also for 1 in minus 1. And other than that, I didn't use anything. Here I use it's 3, by the way, but 3 and 1 are the same for that matter. So we really understand all the places above these. Not sure how it's like impressive to you, but you see it's like an abstract thing. Now I understand them to some extent. And again, what do we mean understand? We don't yet understand, so we don't know how to represent them and so forth. I'll talk about it next. But at least we know there is 1 prime above each of these primes and no other, and E is 2. So what about P2, for example, right? Let's say you have 2 as an element in the field. So what about P2? Then here it won't help you to do these tricks. I mean, I don't know, maybe you can do another trick. I tried, I couldn't, but maybe you can. So let's try to do it the same. So you want to understand prime divisor capital P over P2, like x minus 2. So maybe you want to start the same as I did before. So you take V capital P of y squared, it's 2 times V capital P of y. And y squared is this thing. And now this is an element in the bottom function field, so you can do the ramification index times the valuation of 2 of this thing. But then the valuation of 2 of this thing is what? It's 0, because I mean, at least maybe not, maybe in one field or something it's not, but usually it's 0. I mean, unless the characteristic is 3 or something. Usually it's not Usually it's 0, because when 2 is not 1 minus 1 or 0, this is not, doesn't vanish at 2. So you get a 0 here, which kind of obfuscate E. So you can't say anything about E.
Because a function has no zeros in.
Yeah, exactly. So you need to choose another function that has a 0 too. You can. And then you need to look at the corresponding, so that's a function in X. And then you try to look at what does it mean in terms of Y, and you can do those tricks sometimes, but in this case, I really weren't able to. And actually for that, it turns out, actually that's kind of what we're going to do next, without proofs for now, where it actually turns out to be like arithmetic dependent. So it turns out that whether or not the ramification index of a prime divisor above P2 is 1 or 2 depends on the field, like the constant field that you have. And without a proof, this is what's going to happen. If t squared minus 6 is what happens when you plug 2 to x cubed minus x. 6. So if t squared minus 6 is irreducible, so if 6 is
How do you get 6?
right, it's just x. I just plug 2 into x here. So it's not weird 6. Plug in 2 into that expression, and so you essentially look at this equation modding out by x minus 2. So you look at y squared or t squared generally minus 6. So if this is irreducible, then there is a unique prime divisor line above P2. In this case, and in this case, f is 2 and e has to be 1 because their product has to be 2. And if it's not irreducible, that depends if 6 is a full square, like a complete square in your field. Quadratic, there is a name, quadratic residue. A square, just a square. Yeah. If it's a square in your field or not. Like in F7, I think in case 1, you're F5 in your in case 2. F7 you're case 5, F5 in case 2. I think it depends on 1 or 4, anyhow. And in the other case, where it's not irreducible, you have 2 prime divisors lying above you. So the other case is like that, when E and F are 1. So if you were able to do these tricks, somehow you had to be able also to distinguish between these two cases. And I'm not sure how you could do that. So maybe you need more tools. In our case, it means that for this prime, no matter what the arithmetic is always 1, but it could be that f is 2 or 1. Right, so yeah. And it's not clear, like, how to see that from what we did. And I also should say there is nothing special about x. We kind of want to understand f of xy modulo that. And when I say that, I mean, the right thing. You look at f of x, you look at k of x, you adjoin y, and you mod out by this, which turns out to be an irreducible polynomial, and then you take the fraction field. I mean, what we did at the beginning. So, but I'm just going to say, you look at k of xy modulo by that equation, and that's what I mean. You have these two algebraically dependent variables. And we studied the places of this function field using x. But these places are just there. They are not dependent on x. X was our tool to study what appears here. Because we understand k of x. And so we kind of projected down to k of x, and from there we moved up. But you can do it from k of y as well. You can decide that you are going to understand the divisors of the function field by extending k of y. And you'll get the same prime divisors, but not the same structure. Because when you extend from k of y, you get these will be technically also places of k of y, because it's also the rational function field, but it's not the same P1. It's the P1, it's like the P1 corresponding to y minus 1, not to x minus 1. So you can choose who are you taking. So for example, right, you can try to find, let's do that example also, it's just for fun. You can try to say, I'm going to study my function field f, like starting from k of y. And again, maybe I want to look at the place at infinity of k of y. And let's call it q, just to distinguish it from the p that we have, p infinity of k of x, because it's a different place. This is like where one of x this is where x is not defined, this is where y is not defined, right? It's different things. But they are isomorphic, but they are different things. So you can start at q infinity of k of y and ask, what prime divisors do you have above it? So you can do the same trick, but now x is the new variable, not y. So for example, that's a good place to start. You can say, well, if there is some place p prime that lies above the usual q infinity in k of y, then we know this equality is true because y squared, this is the relation between y and x, y squared is x cubed minus x. And what can you say about this thing? I mean, y is now the x, now is the bottom one. So vp prime of y squared is the ramification index when you go down to the place at infinity, the usual place at infinity of k of y times v infinity of y squared. This is -2, because y has two poles at infinity according to the right infinity, to q infinity, which is, and so you get -2 times the ramification index, and I called it e because I'm lazy. And so if you compare these two now, because both of them are equal to that, you will get that -2e is this thing. So again, keep in mind, x is the new thing. You don't understand it. Psychologically, you're used to x and not to y, but now you're used to y and not to x. And now actually something nice happens here. So here, I cannot like a priori say that this is the minimum of the valuation of each of them. Only that there is some, we have the triangle inequality, not the strict one generally. So this at least is at least the minimum between these two. And again, my goal was to understand E, but so that's not a great thing to have. I want equalities, but for a moment, I can only say that this is at least the minimum between the valuations of the two summons. Of course, minus doesn't matter. So there is a -6, but it doesn't matter the valuation. But the point here is that, this thing is 3 times the valuation of x. So I copied it again here. So that's what appeared before. But the point is that looking at it in retrospect, you know that this is negative because it's at most -2e is at least 1. So this is negative, and it couldn't have possibly been negative if this weren't negative. This wasn't negative, right? Because then the minimum will be at least one of them, which is non-negative. So in retrospect, you know that this is negative. And because this is negative, it's different than that. It's 3 times that. And so actually you get equality here. You see what I mean by not math? Engineering, that's exactly what I mean. Okay, so we actually did get that there are equalities all the way. So -2e is 3 times, the minimum is of course this one because it's negative, so 3 times the minimum is 3 times the negative, it's even lower. So -2e is 3 times the valuation, which gives you immediately that e is 3, because 3 divides that. But then you can say, what do you mean 3? It should be at least at most 2, because the extension is degree 2. It's not degree 2, it's degree 3, because now you extend x after y. So you have k of y, and then you add x. So it's a degree 3 polynomial. All right, so I don't know, I feel it's worth like doing this an example. So you get that e is 3, and you immediately also get, by the way, that phi is -2, but okay.
This is the most case, right?
Yeah, we don't.
Only one point about it. You added like more restriction or something, and you didn't get any new points.
Yeah, we don't like E being large for several reasons. We'll talk about it, but I don't think it's exactly this. Maybe it is. Okay. Okay, good. So there is and by the fundamental equality, by the way, we know that the sum of EI's FI should be 3, and we got one E being 3, so that's the only place above P infinity. And if you want, you can also figure out, for example, what's the divisor of x. Just let's not do it. The divisor of x is just 2 times p 0 minus 2 p prime. Maybe with just one slide. So we got this, if you remember, and we know that e is 3, so this means that p prime is 2, is -2. So like p prime is a pole of like multiplicity 2 of x. Right? Yeah. And the extension of f over, I got back to, yeah, good. And the extension of f over kx if you remember, it's the degree of, it's like how many poles X has. It's the degree of X. And f over kx is the degree 2 extension, right? So this means that we actually found all poles of X. So the pole divisor of X is 2 times P prime, that place at infinity above the usual Q infinity. And if you want, you can also show that the 0, it has only one 0, P0. It's the 1 0 that above 0. Sorry?
Beta prime is, how do you get beta prime? It's like the...
Beta prime is the unique place above Q infinity.
Okay.
Yeah, that's what we did here. It's the unique place above Q infinity. So there is like only one place at infinity in F when you think of it over K of Y. There is no notion of infinity. I think a subtle point. So there is no point at infinity generally. Like there's the rational function field. The rational function field has a pole at infinity. Like depending, it's like where 1 over x is 0. There is what we call place at infinity.
So it's just a place, not corresponds to any point in K of X.
Right. Exactly. And now when you extend it, you have x and y. Then what is the point at infinity? So technically, what you'd want to say is look at the point, like the place above p infinity. But maybe there is no one place. Maybe there are several places above p infinity. And there could be many. But if there is one, we call it the place at infinity also, like as a slang. If there are several, it's kind of the line or whatever at infinity, and so forth. It's not a line, it's part of a line. Yeah, anyhow, so what I tried to do here, hopefully it helped, is to just show you how you can use valuation like arithmetic to understand prime divisors above prime divisors. Good, but let's go into more depth. Let's try. What I want to do now is to actually continue that example and increasingly show you more tools that will enable you to continue where you get stuck with, at least where I get stuck with current tools. I guess you can go a bit further, but you live once and have a job. I can just compute valuations of it.